So far, we've been looking at the motion of a particle starting from its position. So we've said if we know the position, let's say x is a function of time, it's t squared plus 32t or something like that, and we want to know the velocity, then we would take the derivative dx over dt to get to the velocity. And then if we want the acceleration of the particle, we would take the derivative again. We would say dv over dt is equal to the acceleration. But it's actually quite a bit more common in the real world to start here at acceleration and to move backwards. And the reason for that is because of the physics. So for example, the motion of a particle, let's say a particle is dropped off the side of a building or something and it's falling down, the acceleration of that particle will be governed by gravity, where g is equal to 9.81 meters per second squared, or 32.2 feet per second squared if you're in imperial units. And so it's a lot more common to start with acceleration, in which case if we want to know the velocity and position, we would go backwards by integrating. And again, you could integrate here. So there's different ways that this can happen, and it kind of depends on the information that you're given in your problem. So if you have acceleration, so this is the first option, acceleration is given in terms of time t. Then we actually use the same equation that we had before. We had acceleration is equal to dv over dt. Here, we know we have to integrate, but right now we have two integrating terms on one side, and we know that our acceleration is given in terms of time t. So if we want to take the integral of our acceleration, we want to move this dt term up here. So we end up with is a dt is equal to dv. Now, because we've separated our integral, we can integrate both sides. And so you end up with the integral of a, which in this case, I'll just make this a bit more obvious. It's a function of time, dt, is equal to the integral of dv. Now, as you remember from integration, if we leave these as indefinite integrals, so indefinite integrals means we have no bounds here, it means we would have to carry those constants c. So in this case, we're going to add initial values. So here, we're always going to start at time t is equal to t0. I should rephrase, there's situations where you don't start at time t equals t0, but this usually you do. So usually your bound here is equal to 0, and you're integrating up until the time t that you're interested in. And then for v, you start at v0 up to the velocity that you're interested in. Now, it's really, really important that your limits are aligned. So whatever your lower limit is on this side, it has to be aligned with your lower limit here. And then this time t has to be aligned with the velocity here. So it seems really obvious, but there'll be problems where it comes up where you have to make sure that your limits are aligned. Since the integral of dv is just going to be v, we can rewrite this equation as v minus v naught is equal to the integral from 0 to t of your acceleration, which in this case is a function of time, with respect to dt. So this is how you would solve it if your acceleration is a function of time. Now, if your acceleration is given in terms of x, so I'm just going to move this up. So our second option is acceleration is a function of x. So now the equation that we had that related position, velocity, and acceleration was a is equal to velocity dv over dx. So we derived that equation in a previous video. So now we just rearrange this equation. We end up with acceleration, which was a function of x, times dx is equal to v dv. Now when we integrate this, it's only a little bit different. So here we integrate both sides, but now we're integrating from x naught to x, and we're integrating from v naught to v. Now this integral here for velocity is only slightly more complicated than the previous one. So what we end up with is v squared over 2 minus v naught squared over 2 is equal to the integral from x naught to x of acceleration, which was a function of x, dx. Now the third option is when acceleration is given in terms of velocity. So acceleration is a function of velocity. Now this one is a little bit more interesting because in this case we can actually go in two directions. So if our acceleration is a function, so our acceleration is equal to dv over dt, or our acceleration is equal to v dv over dx. So in this case, if our acceleration is a function of velocity, it means that we can use either of these equations depending on if we want to gather information about time or gather information about x. So let's say the question, we have an acceleration. Acceleration is equal to, let's just say v squared, for example. If I plug this value, v squared, if I plug this into this equation and integrate with respect to time, so let's just do that. Let's say v squared is equal to dv over dt. Here we want to get our variables in the right side, so we'll bring our dt up here and we'll bring our v down here. So then we have dt is equal to dv over v squared. When I integrate these, what I end up with is I'll have information on this side about the time and information on this side about the velocity. So if the question is asking me at what time is the velocity equal to something, then this is the equation that I want to use. But let's say we have the same equation, so we had acceleration is equal to v squared. If I plug this now into this equation, I'll end up with v squared is equal to v dv over dx. I'll get all my variables on the right side, so here I'll bring this v squared down, I'll bring this dx up, so then you have dx is equal to 1 over v dv. So now when I integrate this equation, I end up with information about position on one side and information about velocity on this side. So if the question says, when the particle is at this position, what's its velocity? This is the equation I would want to use. Whereas on this side here, the red side, we were linking time and velocity. And so you have to really think about what is the question asking you and what information do I need to get out of it. So in this case, if the acceleration is given in terms of velocity, we can actually choose the type of information we want to get out of the problem. So I'm going to copy in a chart here that has a summary of what we've covered so far. So this chart summarizes all the equations that we've looked at so far, and then next we'll go through some examples so it'll become a little bit more obvious how these equations work.